You can hear me. Giù questo. Credo funzioni. Yeah, can you hear me? Yes? At the back? Yes.
Okay.
Thanks. So I'm going to start with a question, and I know already the answer. I'm going to ask you how many of you have ever had an X-ray? I was expecting a little bit more than you, but that's not good. Well, that's good. Or good, no good, I don't know. We all know how they look like, don't we? We know that they are white and black. There's some gray. We know that white are bones. We know gray parts are tissue, represent tissue. And we know the black part, like Homer's brain, is emptiness or air. So what I'm going to do today is trying to have a chat with you about the physics behind the creation of images like this. And I think I've got an ambitious plan to talk to you, to take you up from X-rays to gamma rays, so computed tomography, to emission tomography. And then maybe I will need to stop at some point, because I don't think I've got enough time to cover everything. But I'm going to make a pact with you. If any of you is interested, if I cannot finish and any of you is interested, just come and grab me, and I will finish the talk with each of you who is interested. What I would like you to do is to learn at least one thing from today, from the next hour. Okay? Well, I hope I will manage that. Which imaging technique do you know, apart from X-rays? Any volunteer? For sure you know ultrasound, magnetic resonance images. And what they all have in common, X-ray, CT, MRI, ultrasound, is that they give you a picture of an object inside a person or an organ inside a person. Probably not all of you know that other type of images. These are morphological images. They give you an image of an organ within a person. These images are functional images. And what they tell you is how our body functions, and if it's functioning properly. So my aim is, some point today, to get to these kind of images. But we can start from this one and just tell you a little bit what this is. And you've seen already something similar, I think yesterday morning with David. This is a positron emission tomography image, a PET image. And we acquire that by giving some radionuclide to the patient. And what we do is we attach a radionuclide that is going to decay positron to a drug. And the drug will target certain receptors in our body. In this image, the drug targets the receptors in these little parts of the brain. And those are the striata. And I'm sure you've recognized that that's the brain. And you do have, even in this kind of images, you do have some information on the morphology. So you can see the skull, for example. You can see where the striata are and the shape of them. But most of the time it's because that information comes from the scatter. And if you create an image with radiation, most of the time you don't want scatter. But in this kind of images, it's quite useful. So it gives you more or less what we are looking at. The information in that image is not, this is the brain and these are the striata. It's how much radioactivity is within the striata. These striata are your motor sensor center. And people, for example, with Parkinson's disease will have less uptake on those two organs, your brain, because the receptors in that striata are not going to be functioning. And in fact, if you know any person with Parkinson, what do? They stumble, they shake, their head shakes. Motor sensor center. Actually, this is an image from a patient who's got dementia, but doesn't have Parkinson's disease. He's got Alzheimer. And the way you can distinguish between the two is by taking images like this and say, oh, the striata looks like they should look. And we call them commas. The striata are a center of something else. They are your reward center. And I haven't mentioned yet which receptors you're going to activate in the striata. Because as soon as I tell you which receptor you activate, which receptors your drug is going to attach to, you're going to understand the function of that little organs in the brain. And the receptors that they activate are dopamine receptor. This is our reward center, the part of the brain that is going to light up when we eat chocolate. Or that's the part of the brain that is going to light up when you take cocaine, you take drugs. What does it do? Is a dopamine analog. It will go and attach to that little striata. The bad side of that is that if you take cocaine, it will go in that little corpuscle in your brain. It will damage it. So the effect that you will have, if you keep using it, is that you will have some symptoms like Parkinson's disease. So you will dementing like somebody who's got Parkinson's. Do you know what a placebo is? Yes? Show hands. Placebo? No? I was expecting more people to know what placebo is. Placebo is a substance that actually doesn't have any effect on us. But if I give it to you and I tell you, drink this glass of water, it's not water, it's a fantastic drug that is going to cure you from your migraine will go. Why? Because actually, the only action of thinking that is going to work will activate our dopamine receptors. So there's less uptake of radioactivity because part of the receptors are occupied by the dopamine that we've been producing just because we were thinking that that glass of water was doing something good to us. So hopefully we'll get to how these images are created. And what I will try to do is to link the creation of images using radiation to what you've learned so far in the past 2 days. And actually, you already know how these images, the PET images, are created. They are created by positrons. And I'm going to give you another piece of information. If you want to create an image using radiation, the type of radiation you want to use are gammas. Do you know, or photons, do you know the difference between positrons and photons? Why would you use photons and not electrons? Anyone volunteer? The reason, yes. Photons are lighter than positrons. The reason why you use positrons, and that's what you use, is what, and I'm trying to remember who told you, I think it was David yesterday morning. Oh no, it was Antonio on Monday afternoon. Positrons, what are positrons? The antiparticle of electrons. So if I produce positrons within human body, what is that positron going to do? It's going to meet an electron, interact with the electron, and annihilate. So the positron is going to disappear, an electron is going to disappear, but what are we going to get? 2 photons. Why? for conservation of mass energy, Einstein equation. And since what happens is that the probability for the positron to interact with the electron is higher when the positron is at rest, when it's not moving, the momentum, the total momentum of the system is zero, or very close to zero. So if my positron and my electron disappear, and I create two photons that are moving, what else needs to happen? The momentum, the total momentum still needs to be zero. So the two photons are going to have the same momentum in opposite direction so that they can cancel out. And for photons, the relationship between momentum and energy, it means that they will have the same energy if they go in opposite directions. Which energy will the photons will have? If I start with a positron and an electron, basically with kinetic energy equal to zero for both of them, what is the mass energy of the system? Einstein equation. 2 times the mass of the electron, c squared. Why 2 times the mass of the electron? Because the electron and the positrons got the same mass. And that is before the interaction. So what's the energy after the interaction when I don't have any mass? Because the photons, they don't have mass. The energy of the 2 photons together needs to be 2 times the mass of the electron times c squared. And we said for conservation momentum, they will have the same momentum in opposite direction. They will have the same energy. So each photons will have half, 2 times the mass of the electron c squared. So each photon will have an energy of mass of electron, speed of light squared. And if you remember, that's a number that has already been given to you. And if you will do physics, it's a number that you will always remember is 511 keV. And I know that you understand me when I say keV, or 1,000 times the electron volt. So when I inject a radionuclide to a patient that emits positrons, what actually I'm doing is to force those positrons to interact with electrons because we are made of atoms. That will happen, and that will happen with high probability, or 100% probability, and very fast. Because that positrons will emit an electron almost immediately. And what they will do is produce 2 photons in opposite direction. But this is not the entire story. Most of the time, that's what they do. And that's what we assume when we go and reconstruct images like that. So that's our assumption, that the positrons decelerate down to a speed of 0, interacts with the electron, gives me 2 photons in opposite direction of a certain energy. But that positron that will be emitted with a certain kinetic energy might interact even before it gets to rest. The only difference is that the cross-section of the process, and that's another word that you already heard yesterday, is much lower than the cross-section of the process when the positron is at rest. So having 2 photons at 500 keV in opposite direction is what happens most of the time. And hopefully I will get to a point where I will tell you why it is important that they are in opposite directions. Because that information is going to help me to determine where the positron was produced. But again, I haven't told all the story. What we can do, well, of course, when we reconstruct these images, what we reconstruct basically is where the photons have been created, because what we collect is the information on the photons. So what we reconstruct is not where the positron was emitted, but where the positron interacted with an electron. Okay? So I need to, if I want to know where the positrons are being emitted, which is the information I want, the positrons are going to be emitted where the radionuclide is going to attach to the receptor. So if I want the position of the receptors, I need to know where the positron has been emitted. How far the positron is going to travel before it's going to interact with an electron, that's an important information. It can be up to millimeters. So I'm going to get this position wrong if I don't correct for that. And what I can do is making an educated guess, knowing that in that material, the positron emitted by that radionuclide has got that energy will travel more or less that distance, or in average, that distance before it interacts. So what I do is called technically a deconvolution. I can go back and tell, okay, I know the photon is being produced here, but actually the positrons was produced anywhere in this area around that position. So just to tell you that we got pretty pictures, but there's a lot behind them, and that's what I will try to describe today. But so far I have been rude. I haven't even introduced myself. So, you know my name, you know that I lecture in Wollongong, and I had to put a picture of our beautiful campus in Wollongong. And this is just one of the ponds we got in the campus. And it's really beautiful. So I think your first question is, where is Wollongong? And this slide is one of the slides I usually use for our discovery days at the university, when we got year 12 students coming to the university, and they have to decide if they want to do physics, if they want to do straight physics, so quantum mechanics or theoretical physics, or they want to do medical radiation physics, which is my background. That's my specializations. And you got things like just to attract them, oh, we are a very cool university, we are on top 2% of the university. But actually we are a young university, and we got to different sites, even one in Dubai, and Wollongong, and I'm sorry that they couldn't switch this light off. But Wollongong is down there. And that's where all our students, when they graduate, usually to go and find jobs. And I don't know if you talk to the students coming from Wollongong and ask them where Wollongong is. It's 100 kilometers south of Sydney. So you can put a position to it. And in Wollongong, University of Wollongong, we got the biggest group of medical radiation physics in Australia, New Zealand, and Southeast Asia that I'm lucky to work with. And we collaborate with a lot of people as well, and that's why that's the picture. It's me pitching to the student, come to Wollongong, we are cool. So you know where Wollongong is, and I bet the Italians know where I'm from. Any guess? Trieste? Yes. Trieste, Bora. Yeah, that's the main characteristics of my town, very strong wind, that even the one in Wollongong doesn't really compare. Why I'm telling you where I'm from? Because I've been asked to tell you a little bit about myself and to link a little bit to Davide, who was talking to you about, or was trying to inspire you, being inspired himself. So I come from a place that looks like that. It's on the coast, North Italy. And we got a beautiful drive from the town, actually I'm from, Monfalcone, to Trieste, where I went to the university. But I did the university there, but before going to Australia, and that's Wollongong, I went to the UK. So everything Davide was telling you yesterday about the job opportunities, I could recognize myself into that. Because I did nuclear physics in Trieste, and then I decided that I don't know, research was too much. And I had a degree in physics, so what I did was programming. I found a job in programming. So it was quite easy. Just next day, oh, I don't want to do physics, I go programming. And after a while, I got bored. I liked more the challenges of solving problems. So I went to the UK to do a PhD. And then I did a postdoc in London. And then I found a job in a hospital. So I work in a hospital as well. And then for family reason, I moved to Australia, where I found, again, a job in research. So physics opens you a lot of doors, if you want. You don't need to do just one job. And of course, we've got even a bus to drive down in Sydney. And I bet you've seen this driving some commercials around the world. And you can recognize this. It's beautiful to drive through that. So what am I going to talk to you about? I think I've got time just to talk to you about physics. I wanted to relate it a little bit more on imaging, but I might not have the time to go that far. So I'll just probably go and start from a little bit of history, tells you how modern physics, or why modern physics is important in medical imaging. And hopefully tells you how images are created or formed. And you've seen these images already. And this is, again, another PET image. Where does it start, or medical imaging? It starts with these guys. 22 of those guys had the Nobel Prize. Okay? And you can recognize Einstein, Marie Curie. And I want you to remember 3 names: Marie Curie, Einstein, and Compton. And of course, all the other guys were important for the development of the job I do as well. But these are 3 names that I'm going probably to mention later on. And then I put this slide the other day, and I thought, maybe I don't need it. But this is a question I get a lot from my students. I lecture modern physics as well at university, which starts in 10 days. And well, I get 2 questions from my students. The first question is, why is it called modern? Something that has been discovered a century before you were born. I don't have an answer to that. Sorry, it's still called modern. I know, it's kind of an ancient for you. And the other question is, why do I need to learn modern physics? Especially because a huge group of my students are going to do medical physics. And I said to me, why do I need to learn modern physics? Like, can I just skip and do just the interesting stuff? And then they say to me, well, classical physics works. We can send probes around the universe. And again, I'm sorry, you cannot see the image very well, but... And then I tell them, look, take this slide at the beginning of the course, keep it to the side, and then go back to it when you finish the course. And you will see how all this stuff relates to each other. And I don't want you to read all this because it's too boring. But here it says photoelectric effect, then you've got Compton scattering, and you've got relativity somewhere here, and you've got Schrödinger equations, and hopefully I will mention Schrödinger equations as well, and why they are important in nuclear medicine physics, which is my field within medical physics. So where all this starts, and you've seen these images before, haven't you? Several times in all your textbooks. One of the first X-rays, Röntgen's wife hands. Do you know how he discovered the X-rays? He was, being a physicist, I think he was playing around more than investigating. I like more the term playing around with a type of rays, the cathode rays. But when he was studying the cathode rays, he didn't really know that there were electrons. So he had an instrument like this, and what he was doing was having some current going through it. He was producing the cathode some rays, the cathode rays, and then what he noticed was that when they were hitting this part of the instrument, this is vacuum, so it was bending the electrons. This was fluorescing, but then was something coming out. And if it had a screen, that screen was reacting to whatever was coming out from this part of the instrument. He didn't know what they were. He called them X-rays. And no, I don't know what they are. I'm calling them X. Few months later, his discovery, and then he discovered that if you put something between here, you can take a picture of like the bones of the hands, and you can see inside objects. Few months after the discovery of the X-rays, I think it was late 1895, at the start of the 1896, people were already taking X-rays. And then you've got all the development of images going from, oh, I can add some contrast into the patient and I can see better. And I hope I will get to the point where you understand why, if you add barium, you're going to see things better. And then you've got nuclear medicine imaging, which is the poor sister of medical physics. You know, when somebody talks to you about medical physics, everyone is thinking about CT, MRI, radiation therapy, and no one talks about nuclear medicine, but actually we started imaging with radionuclide before CT and PET. And then you've got in the 70s, early 70s, you've got the CT, the PET, and then people start putting stuff together. So what physics knowledge do you need in order to be able to take an image using radiation? First of all, you need to be able to create photons. And now I remember that I didn't ask my question. And my question was, why do you use photons to take images instead of electrons or alpha particles? If I create a beam of electrons and I shoot a beam of electrons towards a patient, what do you think is going to happen to the beam of electrons? They are going to be absorbed, sorry. Yeah. The two bad things are, one is they are going to be absorbed by the patient, so you don't see through the patient. And the other bad thing is because they are being absorbed by the patient, you're giving what is called dose to the patient. So it's going to deposit all the energy within the patient, and by depositing energy, it will break cells, basically. So you are going to provoke some damage to the patient. And for alpha particles, the same. So we need photons. Why? Because photons will go through the patient. If you think about an X-ray image, they go through a patient in different ways, depending which material they are going to traverse. So you will have more through soft tissue and less going through bones. So first of all, we need to know how to produce photons. And from classical physics, you already know how to produce X-rays. And you've heard this already a couple of times in the past 2 days. If you got a beam of electrons that are going to be decelerated, the electrons, so they are going to be bended for any reason, the electrons are going to produce, well, they are going to lose energy, and that energy is going to be converted in the production of X-rays. So if I'm able to decelerate electrons, I'm going to be able to produce X-rays. Another way is to use radionuclides. And you can already see the two branches. One is X-rays images, so X-ray projections and computed tomography, and the other one is gamma, which is nuclear medicine, or positrons that eventually will give you photons. So I can use unstable nuclei that will emit gammas. I know they will emit electrons or beta particles and alpha particles as well. The other information I need to know if I want to be able to make images using radiation is how this radiation is going to interact in the object. And we said we can make an image using X-ray if some of the X-ray are going to be transmitted and some of the X-ray are going to be absorbed. And that mechanism needs to be different for different material. So the photons can be absorbed, and that is the photoelectric effect that's been explained by Einstein. They can be deflected, so change direction, by not losing energy. It's a relay scatter. They can change direction and lose energy. Compton scatter. They can produce pair. Do you know what is pair production? Yeah. Yes. Photons, I'm trying to work out if I need, I will explain that. I've got an image or the slide in a few minutes, so we can discuss how that happens. But yes, it's a production of matter and antimatter, or electrons and positrons. So you already know how X-rays are produced. I've got an electron incident to an atom. Depending how far from the nucleus this electron is going to travel, that will determine how much energy the electron is going to lose. So in a kind of a head-on collision electron nucleus, what is going to happen is the electron is going to lose all the energy. So how much energy the X-ray produced, or the photon produced, is going to have? That's my question to you. You've got an electron with a certain electron volt energy. What's the energy of the photon if you've got this type of collision where the electron is going to lose all its energy? Well, if it's going to lose all its energy, the energy of the photon will be the energy of the electron, of the incident electron. So that's the maximum energy at which you can produce the X-rays via Bremsstrahlung. Because the electron is not going to be able to lose more energy than it possesses. But if the electron is going to be decelerated farther away from the nuclei, it's going to lose less energy. So the photon that is going to be created is going to have less energy. Let me go to this slide. So what you do when you've got a beam of electrons incident into the material with millions of atoms, the type of interactions close or farther away from the nuclei is going to be, well, all the ranges. But the probability of head-ons interaction is going to be lower than the probability for the electron to lose energy farther away from the nuclei. So actually what happens, you create photons with energy from 0 to the maximum energy of the incident electron. So imagine a line going up like this. So you will have more X-ray photons of this energy, close to 0, and less photons up to the energy equal to the maximum, or to the energy of the electrons. Don't consider the spikes at the moment. What do you think happens here? And I'm going to go back one slide to show you how the X-rays are produced in an X-ray tube. First of all, if I want to create X-rays, I need electrons so that they can be decelerated in a material. the way I produce electrons is by running current in a filament. What actually I'm doing is I'm giving energy, thermal energy, to the material in the filament. And by giving thermal energy to that material, to those atoms, what I'm doing, I'm freeing electrons from the filament. Once I've got these free electrons, what I do, I apply a difference potential. What does that do? It's going to accelerate the electrons when they are freed. Basically, they don't have any speed. They are going to be accelerated up to a target from the cathode to the anode. Which energy are they going to have? I'm just hearing part of the answer. I'm sorry. Yes. So you've got the difference in potential, so it will be equal to that. But the other thing you've learned in the last 2 days is a new unit to express energy. And this is the electron volt. So it's the production of the electron charge times the difference in potential in that part. So what happens is that if I apply a different potential of 100 kilovolt, which is typical for X-ray machine in a hospital, the electrons will be accelerated to an energy of 100 kilo electron volt. So the electrons that hit my target material will all have more or less, and when we talk about physics, we always talk about average numbers. So in average, the electrons hitting the target material will have an energy of 100 kilo electron volt. So the maximum, if this is 150, it means that I applied a different potential of 150 kilovolt. So the electrons will have this energy, and the maximum energy for the photons will be this. What happens to these photons coming out of the target? And the target, and I'm sorry again, you cannot see, but is relatively big. So it's got a certain depth of 0.5 centimeter. And all your photons are being created within the target. What happens to these disappearing photons? These are the photons that are being stopped within the target. They don't have enough energy to get out. From the medical perspective, point of view, if I have to produce X-rays using an X-ray tube, I'm kind of happy that that happens. Okay? Why? Simply because if this is the photons and the energy the photons are going to have in exit of my X-ray tube, I'm losing photons at low energy that will have no probability, very low probability to leave the patient. So if I'm shooting these photons towards, or X-rays towards the patient, they will be absorbed by the patient. And again, it's like the electrons earlier. If they're being absorbed within the patient, they are depositing energy, they are creating damage to the patient. And if they don't transverse, they don't go through the patient, they are not giving me any information. So they are useless to me. And we will see what those spikes are later on, but remember those. So that's how I create X-rays. And the message here is that when you create X-rays via Bremsstrahlung, and this is the X-rays you've got in an X-ray machine in a CT, or for your X-ray image, you've got a range of energies. Okay, they don't have one single energy. And that's another thing to remember, because I'm going to need that in a bit. So we said two ways to create photons. One, X-rays, and now we know how X-ray works. And the other one is using unstable nuclide. In nature, there are not a lot of stable nuclides. Well, all the nuclides we got, or atoms, are stable. And the blue nuclide in this chart. Down here, you've got neutrons, and there's protons. So each point represents a nuclide of a certain number of neutrons and a certain number of protons. So if they got this combination, neutron and protons, they are stable. In nature, you've got some unstable nuclide. Can you name some? I mean, natural occurring radionuclide. The most simple one, uranium. Yeah? Another one? Thorium? I missed yours. Radon. And I give you another one, and let's see if you know it. It is in your bananas. Potassium. All the yellow ones here in this chart are man-made. And if they are unstable, what they need to do is to go to a stable state. So if they are up here, they've got too much mass. And they want to be down here, okay? So if the nucleus has too much mass, what does it need to do in order to become a stable nucleus? Simple question. It will need to lose mass. And one way to lose mass is to expel protons and neutrons. It can expel alpha particles. What is an alpha particle? It's a helium nucleus, 2 protons, 2 neutrons. And I asked you to remind me about the Schrödinger equation. That's where it comes into it. The description of the alpha decay can be explained by the wave nature of the nucleus. The fact that an alpha particle that can leave the nucleus can be explained only by tunneling. You will learn that, depends, in Australia, we will learn that next year for you guys. And I think in Italy, it's been learned in the 3rd-year university how to solve the Schrödinger equation and calculate the probability for the nucleus to decay alpha, and how long it will take for that nucleus to decay alpha. If the nuclide is down here, it's got too many neutrons. So if it's got too many neutrons, what does it need to do? If I got too many neutrons, I need to lose a neutron. And the way you lose neutrons is actually by converting a neutron into a proton plus an electron. So what happens to the nuclide? If I transform a neutron into a proton, the chemical element changes. So I end up with a different element, plus an electron. So I'm emitting electrons with a certain energy. And when people studied this kind of decay, they realized that the story was not complete if you had the emission only of the electron. Because again, you've got the electrons that will leave the atom or the nucleus and will have a certain energy and especially a certain momentum. While the nucleus will have small momentum, but not enough to conserve the momentum of the system. So the momentum of the system before decay was 0. The nucleus was happy in its position, was not moving. Then suddenly it decays, emits an electron. The electron's got momentum. The nucleus moves a little bit, but not too much. What do I need to conserve momentum? I need another particle. So theoretically, they predicted the existence of the neutrino. And the same story if you are up here, where you've got, what? Too few neutrons to get into this blue line. So if you've got too few neutrons, what do you need? You need to acquire one. If you're down here, your neutron becomes a proton plus an electron. If you're up here, what do you think happens? I need a neutron, so I will need a proton to become a neutron plus a positron. And again, for the same reason as down there, to conserve momentum, I will need a third particle. And I don't remember, I have to admit, I never remember if the antineutrino is produced with this reaction, with the beta minus or the beta plus. I always need to check. But you will produce a neutrino which is opposite to the antineutrino of the one produced in the other decay mode. So now we got X-rays. Oh, I was forgetting the most important one, gamma emission. Do you know when a radionuclide will emit gammas? It's very similar to the situation, I think it was Monday afternoon, when the Bohr atom was explained to you, the fact that you've got quantized states. And if you consider the hydrogen atom, you got your proton, you got your electron. The electron is happy at the ground state, 13.5 electron volt, but then for some reason can be excited to a higher level. If it's excited at a higher level, orbit or shell, how you want to call it, what the atom will try to do is to go back to the ground state. So the electron will jump back into the ground state. And when it does that, what does it do? Because it's got a lower energy in the ground state. It's got higher energy, needs to lose energy. The energy that in excess will leave the atom as the photons. Yeah. So can you think of a similar situation for a nucleus? And what happens is if a nucleus is unstable, and undergoes alpha decay, beta plus, beta minus decay, the end product, most of the time, has got an excess energy. So the nucleus is not in a ground state. It's an excited state. It needs, or it likes, to lose energy, go back to the ground state. And when it loses energy to go back to the ground state, what it does? It emits gammas. And in nuclear medicine, we use this kind of radionuclides to make images for SPECT, single photon emission tomography. So we inject patients with radionuclides that somehow either they undergo beta decay, and then they are in excited state and they will emit gammas, or we create most used radionuclide is technetium-99m, which is a metastable state of technetium-99, which simply means it's not at its ground state. It's an excited state, and will emit gammas. So, okay, I've got the X-ray, and I've got my gammas. Now I need to know or understand how these photons are going to interact with the matter. Who knows photoelectric effect? Who's volunteering, shouting? It seems that I cannot hear you, so you have just to shout. Or shall I go for it? So you got the photons. What the photons is going to do is interact with an electron, and what it's going to do is to give all its energy to the electron, and then the electron will be expelled from the atom. And it's called a photon electron, just to tell people that that electron is being expelled from an atom because of photoelectric effect. Do you think there's a limit on the energy of the incident photon? So the photon incident can have any energy. It needs to have enough energy or it needs to have higher energy than the binding energy of the electrons. So if I want to knock out this electron, we'll have a certain binding energy, and the photon will need to have at least that energy. It's got lower energy, it's not giving enough energy for the electron to leave the atom. And then, do you remember the spikes on the X-ray spectrum? And I told you, forget about those. Now remember them. Let's go back to these spikes. What happens, in your opinion, if you got like a photoelectric effect where a photon arrives, knocks out this electron, inner shell from the atom, so this atom is losing that electron, or you've got an electron coming, giving some energy to that electron, and knocking out that electron. So I'm ending up with an atom missing an electron, and missing an electron in an inner shell or orbit. What do you think is going to happen to that atom? Yes? Yeah. So electrons in the outer shells, one of the electrons, will jump down to that position. And when it jumps down, what else is happening? So the electron that's jumping down has got a higher energy than the bonding energy in that shell. So what happens to that energy? Transforming the photons. So what you have, you've got the emission of photons of a characteristic energy, and that energy is characteristic to the material. It's characteristic to the shell formation for that chemical element. And you remember yesterday Angelo Bassi showed you the spectra, the emission of the absorbed spectra from different materials. You had the hydrogen, helium, sodium, and you have that black band with some colors. And those colors are given by this process. So each element has got its own emission spectra. So these are going to be characteristic of whichever material you're using to produce your Bremsstrahlung. They will have characteristic energies. And actually, by measuring the position of those spikes, you can determine which material you used with some accuracy. Then what happens to the photon? The photon comes, interacts with the electron. Nothing happens to the electron in this case, but the photon just changes direction and doesn't lose energy. So the wavelength is the same for the incident photon and the photons that leave the interaction. And then we got comphoton incoherent scatter, where you got the photon comes in, interacts with electrons, but this time the electrons is knocked out from the atom. So the electron will acquire, again, momentum and energy. So the photon that will leave the interaction, because it's given some energy to the electron, will have lost some energy and will change direction. And it will need to change direction, or the angle between the electron and the photon needs to have a certain relationship. Why? Because of conservation of momentum. And that's what this equation is telling you. Okay? That you need conservation of momentum and conservation of mass energy. And this is the wavelength of the exiting photons, this is the wavelength of the incident photon, and this is the mass of the electron. And this theta is the angle at which the electron is going to be scattered. Pair production. We can go back to pair production now. So you've got a photon that interacts with the field around the nucleus. Nothing happens to the nucleus, but somehow that field helps the photon to convert. Oh my God, I'm almost there. They are going to just shut me up. The photons will convert, will disappear, and will produce a particle and antiparticle, as we said before. What it produces is an electron and a positron. But now we know, and I bet you know, the rules. So the first question is, which energy the incident photon needs to have in order to be able to produce an electron and a positron? Conservation of mass energy. So it needs to have an energy equal or greater than the rest mass of the electron and the positron. So the incident photon needs to have at least 2 times 511 kilo electron volt. Otherwise, pair production cannot happen. And the good news for imaging is that we never use that kind of energy. So pair production doesn't happen. So quickly, and I think I've got time only for 2 slides. And I'm sorry, I haven't touched anything that I was meant to be touching today. So now we know how to create gammas. And we know how they interact. So my question to you is, if I got 1 photon incident into a slab of material of thickness delta x, what is going to happen to that photon? We said that photons can have different types of interactions. They can undergo photoelectric effects. They can undergo coherent or incoherent scatter. They can produce pairs. And to make your task easier, I'm telling you that the energy of the incident photon is not enough to produce a pair. So if I got 1 single photon, what is going to happen? Can you tell? Or what can you tell? What can you say? The only thing you can say is that it could be transmitted with no interaction. That's one possibility. It could be absorbed by a photoelectric effect, so it's going to disappear. It could get scattered without losing energy or losing energy. And once it gets scattered because it doesn't disappear, maybe after that it can be scattered again if it hasn't exited the material yet, or it could be absorbed by photoelectric effect, or it could just keep going and exit the material. So the question at this point is not which process is going to happen, but which is the most probable process. So any of these can happen to that single photon. And the probability for each single process to happen depends, again, on the cross-section of each different process. Each different process got different probability to happen. And the cross-section depends, and that's almost obvious, it depends on the material the photon is going to travel through. For example, if it's more or less dense. and depends on the energy of the photon as well. So what happens if I got n0 number of photons? Each single photon will have a certain probability to undergo one of the processes. But if I know the number of incident photons and I go and count the number of photons that come out of my slab, and they can be absorbed, so they disappear, they just transverse the slab of material, or they can get scattered. If I count this, what I find out is, well, first of all, if I take the difference of how many photons are exiting the slab and how many photons were incident to the slab, that number is negative, because some of the photons are going to be absorbed. So if I take the difference, this difference is it's negative. It's proportional to the number of photons I'm shooting to the material, and it's proportional to the thickness of the slab. And then it's proportional to another number, mu. And I can rearrange this equation, and I can describe what happens with this exponential. So the number of photons leaving the slab will be equal to the number of photons incident to the slab times the exponential of minus the mu of that depends on energy of the material of the slab times delta x. And that mu is telling you the probability for the photons to interact in that slab. And it's called the linear attenuation coefficient, and depends on the energy of the incident photon and the material. And I'm going to skip that. And I'm going to count this so I can conclude on something maybe this is going to be useful. So I've got my X-ray machine, I've got my object, I get my image. And I know that this image depends on how many photons are going to be transmitted in each part of my object. I know that the attenuation coefficient for bones is greater than the attenuation coefficient for soft tissue, which means that less photon will be transmitted through bones than soft tissue. And the attenuation coefficient of soft tissue is greater than the attenuation coefficient of air. So again, less photons will be transmitted through the tissue than through air. So if I want to see details of different materials in my projection radiography, what I need is an energy so that for the material I'm going to look at, the difference in attenuation coefficient is maximized. Am I making sense? So ignore this. This is the iodine. And this is a contrast agent. Okay? This is attenuation coefficient for the contrast agent. And this is the energy. And this is your linear attenuation coefficient divided by the density of the material. The green line, yellow-green line, is the attenuation coefficient for bones. And the red, and underneath that, that's the blue lines, is tissue and lung tissue. And they look the same because it's just normalized by the density. They would be different if you don't normalize by density. But if you look simply to tissue and bone, you're going to see contrast between the two in your radiography if there's a difference in the two attenuation coefficients. The energy used for X-rays to distinguish bones from soft tissue is around here. And the reason why, this is 100 kV. And the reason why I choose 100 kV, because I've got the two situations. One is I have to maximize the difference between the two attenuation coefficients so that I'm able to distinguish the two tissues, bones and soft tissue. And the other one, I've got X-rays going through a slab of patient. And I need them to have enough energy for them to go through. So if they have to go through a patient, they need to have around the minimum, usually is 80 kV. 80 kV is usually used for kids. That's slimmer. So they use 100 kV. You've seen this image on Monday with Catalina. And after I saw it, I asked her to have the slide. And this is a mammography. And she said to you, look at this. If we use synchrotron radiation, we're getting better and better images than conventional mammography. The reason why you do that, or you get that, first of all, better to me, medical physicist, means higher contrast to noise ratio. By using synchrotron radiation, what you are maximizing is the difference between the attenuation coefficients. So in conventional mammography, you use an X-ray tube. So you create ranges of energies, or photons of range of energies. And ignore the blue line. The red line is the one you want to look at. So this is the energy spectrum for this kind of mammographic system. It's molybdenum, molybdenum. And what that means is you've got a target in your X-ray tube of molybdenum. So you've got characteristics, characteristic X-ray to the molybdenum. And then what you do, you add another little filter of molybdenum. And what that little filter, the second MO here, is going to cut more low energy photons, is going to enhance the peaks, the characteristic peaks. So if you've got an X-ray machine that gives you a range of energy, this is a way to try and make it as most monoenergetic as you can. In mammography, there are two things. First of all, what you are looking at, or the contrast you are looking at between attenuation coefficients, are not between soft tissue and bones, but it's between glandular tissue and adipose tissue. I forgot that. So you're looking at two different attenuation coefficients, okay? The other advantage in mammography is that the depth the X-rays or the photons needs to travel is not as much as the depth when you've got an X-ray projection. And I'm sure that no one of you ever had mammography, but maybe your mother had. You squish the breast to take a mammography. And the reason you do that is to reduce the depth the X-rays needs to travel through. And if you do that, what you can do, you can lower the energy of your X-rays or your photons. They will travel through. So by using the synchrotron, what you've got is maximizing this difference in attenuation coefficient. And these are not normalized by density, okay? So normal X-rays, you've got this difference here. With synchrotron radiation, you can lower the energy, and you can maximize the contrast. And that's why synchrotron radiation, monoenergetic synchrotron radiation is giving you better images. And I'm sorry I have to stop here. Do you have any questions so far? Or you can grab me around, we can have a chat. Thanks.